Thanks, Marek. Well, I think threads. I think the jumper has been well. Monday morning, the threads are hanging off the old jumper, I'm afraid. Okay. Right. So, recursion. We're on about here. Now, recursion is, so what we need to do is summate for if you have multiple threads, all right, and you have multiple tasks. So let's say if we've got 1,000 tasks and we have 4 threads. Okay, how do we divide up the tasks more? Now, it will work fine and it will be 4 times faster, but there is a way to make further efficiencies, okay, to make sure that each of those 4 threads, Jesus lads, the most efficient way to do that is that each of those threads does 250 tasks. Yes? Yeah? Right. Now, if you have one thread doing 500 tasks, another thread doing 100, and the rest of them doing 100, that'd be 600, another one doing 200, that'd be 800, and another one doing 200, that'd be 1,000. Okay? That is slower than 4 threads doing 250. Okay? So, what we want to organize how our threads are being used. And you do that by using something called a fork join, which is the data type. That's the actual data type. A fork join. Now, fork join uses, they're actually classes. They're not interfaces. So I stand corrected on that. They're interfaces. One is called recursive action. So you need to extend recursive action. The other one is called recursive task. Okay. Now, both of those use something called recursion. Now, anything that does itself, which sounds kind of weird, is recursive. Okay? So, in computer terminology, it's a method calling a method, calling the same method. So, an example would be if I have an eat method, and inside the eat method, I call the eat method. That's a recursive method. Now, the problem, of course, with recursion, if I just have actually, what I'll do, I'll create a method like that. All right? So, I will just go here. So, I will go to examples. And I will go static void ex3. And I'm going to have a method beneath it. I'm going to go void recursive. And I'm going to have inside here, and I'm just going to say, I'm going to make this static as well. So I'm going to say recursive method called. And if I go here, oops, sorry. Right. So here we have a static method called recursive, and it's calling itself. Now, if I go here, now everything seems okay, right? Till I go to main. Now, so go to the very top. So it goes recursive method, and then it eventually hits on. So stack overflow error, okay? And keeps going on. Now, that is because here we call the method recursive. Okay. And so the first thing that happens inside it, it prints off recursive method called, and then it calls itself, and then it prints off recursive method called, and then it calls itself. There is no way for it to exit. Now, it eventually, after a couple of hundred calls, it says, right, we have no way of exiting this. So it gives us a stack overflow error. Okay. Now, stack overflow error, if you have a recursive call, if you have a method of calling itself and it has no way to exit it, it generates a stack overflow error. Okay, so I'll put in a comment here. So a method calling itself is a recursive method. Okay. However, a recursive method has to have a means of coming to a conclusion. Okay. If not, the method will be called a few hundred or possibly a few thousand times, and will then generate a stack overflow error. Okay. In this example, we call the method recursive, which prints out recursive method called and calls itself again. And if it did not generate a stack overflow error, it would continue calling itself forever. Okay, as we have provided it with no means of exit. So what we need to do is we need some sort of mechanism that determines after a set amount of times it calls itself, it'll exit. Okay, one of the ways is if you have some sort of external counter. Okay, so you can exit if you provide, for instance, an external counter which will cause our method to exit after the counter reaches a certain number. Okay, now this number that causes our recursion to stop is called a base case. Okay, now what we're going to be doing when we're doing these fork joins, okay, I think we have something that takes 20 tasks, 20 different tasks. At the start of it, we've only one person doing the task, and he can only do 3 tasks at a time. So what he's going to do is he's going to ring up Johnny down the road, and Johnny's, come up here and help me. Johnny does 3 tasks. Now, how these task is allocated is by recursion. And the base case is going to be each person does 3 tasks. Okay, so we're working down to a base case. Now it's usually working down rather than working up. Okay, you start off with 20 tasks, you work down to the base case of 3 tasks. Okay, now, so to show you how recursion, we're going to do some calculations. Now be careful with these calculations. Now, the main issue with recursion is, particularly when you're doing multiplication, for instance, is that you can quickly end up with numbers that are impossible to calculate. All right? Or, I think this is an extreme example, you could easily end up with a number that would take more time that's left than to the end of the universe to actually calculate the number. All right? That's the sort of numbers we're talking about here. And they're relatively easy to calculate. That's the thing. Ignoring me. Now, so we shall go back to here. Now, we are going to create a method. So we're going to go static void ex4. And we'll leave that there for a minute. Now, right, so I'm going to have a method down here. Now, what we're going to be doing is we're going to be creating a method. We're going to pass it in a number. Let's say the number 5. Okay, pass it in the number 5. What it's going to return is it's going to be 5. So we're passing the number 5, and then it's going to go say 5 multiplied by 4 multiplied by 3 multiplied by 2 multiplied by 1. Okay, is that the Fibonacci sequence? Does anyone know maths?
No, that's not.
What's the Fibonacci sequence?
1, 1, 2, 3, 5.
It's close, isn't it?
Yeah.
Okay, so if I say Fibonacci 3 would be 2 plus 1.
That's just the sequence. You have 1, 1, then 2, then 3, then 5, then 8.
So you have 1 plus 1, 1 plus 2. No. Is it?
0, 1, 1, 2, 3.
Oh, so 0 plus 1, and then you have 1 plus 2.
1 plus 1.
Oh, fucking hell. Yeah, so 0 plus 1, 1 plus 1, 1 plus 2, 1 plus 2, 2 plus 2. Oh, I don't fucking know. Well, fuckers, I don't know. This one is binomial, is it?
Sum of the next number, the next number is the sum of the two.
All right, so 1 plus 0
Yeah.
is 1, and then you go 1 plus 1.
Yeah.
1 plus 2 is 2, and then you go 2 plus 2.
2 plus 3.
No, isn't it?
Yeah.
It's 2 plus 2. 2 plus 2 is 4, so that's 4 plus 3. Oh, fuck it, I think so. I don't know. Fuck it. I'm sorry I even said it. So that's called binomial, Kieran, is it? Okay, so binomial. Right, so if you do binomial 5, that is, actually binomial 4 is easier. 4 by 3 by 2 by 1.
Oh, yeah, that's 4 and exclamation.
Is that?
Yeah.
Okay. Now, possibly that notation might work in Java as well. I don't know. See, but right. What we're going to do is we're going to start off with 4, right? And we're going to produce that sum. So that's 2 multiplied by 1 is 3. 3 multiplied by 3 is 9. 9 multiplied by 4 is 36. So if it was 5 multiplied by 36, that's 100, and so 5 3 is 150, 5 6 is 30, that's 180. Yeah? Right. Now, you need to be careful with these binomials. They get very, very, very big very, very quickly. For instance, the largest binomial we can produce in Java is 65, which isn't that big of a number. If I go 65 multiplied by 64 multiplied by 63, blah, blah, blah. Okay, that's the largest number that can be produced in Java. Okay, now that produces, for instance, now the number is huge. I don't even know how to pronounce it, all right? But we're going to be producing factorial 20. Now factorial 20 produces something called 2.4 quintillion. What's a quintillion? It's 2 and 18 zeros. Okay, and we will be producing this number, binomial 65. Now, binomial 65 produces a number that is, let me just see, I'll just run it here on the machine. Just give me a second. It produces a number that's 2,520 digits long. Okay, which is rather large. All right, I don't know how you pronounce it. All right, so, and that is the biggest number as far as I know that can be dealt with in Java. All right, now, how we produce that is recursion. Okay, we start off with 5 and we keep calling ourselves until it gets down to 1. When it gets down to 1, it exits. Okay, right, so that's the method we're going to be using. Now, so what is the method? So they're large numbers. I'm going to do 2 different methods for showing you recursion. Now, one of them is going to return the biggest primitive data type is long. Okay? Now, that can deal with numbers, that can deal with the quintillion thing. Okay? But if you want to go beyond that, you have to use a specific class. It's called big integer. It's not a primitive data type. Okay? Big integer is not a primitive data type. It's a class. It's a wrapper, effectively. And it deals with extremely large numbers. The number that is 2,520 digits long, which as far as I know is the biggest number you can have in Java.
It's double bigger than the long.
It's bigger in size, but it's not bigger in amount. Does that make sense? Yeah, it's right. So it takes up more memory on your computer, but in pure size, let's say a double, I don't think can go to a quintillion. A long can go to a quintillion, but a double can have thousands of decimal places, whereas a long can't have any decimal place. So the numbers that are dealt with by a long are bigger, but not in memory terms. In memory terms, a double is bigger than a long. Okay. Now, so we're going to go here. We're going to call our methods factorial. Okay. Our binomial is a better one, I think. Static long, I call it binomial. I think that spells it right. And it takes in an integer. I'll just return 0 for now. Okay, just to keep that like that. Now, so what we're going to say is we're going to give it a choice. If it reaches, so it's going to start off, let's say, at 5. Okay? When it's at 5, it's going to call itself. And it's going to go down to 4. If it's at 4, it's still going to call itself. And it's going to go down to 3. If it's at 3, it's going to still call itself and go down to 2. If it's at 1, it no longer calls itself. And it's going to exit, basically. Okay? Now, so if it's at any of those 4 numbers, it's going to call itself. All right? If it's not any of those 4 numbers, it's just going to return the number 1. All right? So, here we go. Now, so clear all drawings. So this is what we're trying to do here. Now, big integers, as far as I know, doesn't take numbers. It takes strings. Okay, as far as I know. Okay, so big integers do not take strings. Okay, it takes, or does not take ints, does not take doubles. It don't, as far as I know, it only takes strings. So whatever this number is, we have to convert it into a string. So we can do that easy enough. We go string str num is equal to num dot to string. Now, I am going to create a big integer. So the data type is big integer, big num. I need to import that. Now, big integer is not on the exam. It's just when you're using the, I'm using this, you're going to get to larger numbers pretty quickly. Yeah, because you can't call the toString method of a primitive. Okay. But you could just as easily go string str num is equal to num plus a blank. That changes it to a string as well. So big integer big num is equal to new big integer. Now, as far as I know, you can't do that. As far as I know, you can't do that. All right. As far as I know, big integer only takes str in um. Okay. So now, the reason it takes a string rather than a number, there's a good reason for that. All right. If you write a very, very big number, now, if you write that number in Java, there's no primitive data type that can take that. All right? Can't be taken. In actual fact, most computer languages won't be able to accept that. C will, I think, as far as I know. All right? The more primitive languages will accept those numbers. But modern languages can't deal with that. You could maybe look on that as a design flaw, I don't know. All right? However, if it's a string, all right? So if you have it as a string, big integer can take that. All right? So there is no primitive type that can take that number. But if it's a string, you can just bung it into there, and now it's a number. All right? Now, ordinary, right. So I'm just going to get rid of all of this shit. Now, I've actually just looking at here, I didn't actually use big integer, but we'll go with it for a minute. All right. So now we want to work down, so we want to give a choice. So we need to have an if statement of some description. Now you could do it as a, what do you call that thing again? Instead of an if statement, ternary operator. Okay, so we could use a ternary operator, but I just find if statements easier. So now I'm going to type it out first and then explain it. So if num is less than or equal to 1, we're going to return 1. Okay, now, so put in here, this is the base case. So we keep decrementing num by 1 until num becomes 1, at which point the binomial method will no longer call itself. Okay, so that's the base case. Right now, so as soon as it reaches 1, it's going to return 1. Okay, now the else part, it doesn't all become clear until I do the else part. So I'm going to do else. Now, so we send the number 5. It's going to decrement it by itself by 1 each time. Okay, until it gets to 1. All right, if it's not at 1, I'm going to say return. And I go num, so if that 5 multiplied by factorial minus num. It's not factorial, it's binomial. Now, you're better off to do this, by the way, than minus num. Because I'm not 100% sure what happens when you go minus num. All right? It might do, I think it does the minus part first, doesn't it? Yeah. So you need to do it that way instead. All right? So this is one circumstance where you wouldn't go minus num. Now, what happens here? So I pass in the number 5. Now I don't use big integer here. I don't know why you put that in. That's not until the second one I'm using it. Okay, so I'll just comment that guy out. Right. Now, so I'll just comment that out. That's for the second binomial method. So I will take it out. This shouldn't. No. Yes, Kevin.
Why did you go binomial num rather than num by?
Because I'll show you. Okay. Right. So we're going to pass in the number 5. Okay. So num is 5. Now, num is not less than or equal to 5. So that's ignored. So it goes down here. So it's going to return 5 multiplied by, it's going to call the method again. Okay. And what's that going to, it's going to return binomial num minus 1. Okay. Binomial num minus 1, that is 4. That becomes 4. So it passes in 4. 4 is not less than 1. So it goes down here. That's 4 multiplied by binomial num minus 1. It's 3. Passes in 3 in here. 3 is not less than or equal to 1. So we go num multiplied by binomial num minus 1, which is 2, passes in 2 in here. 2 is not less than or equal to 1, so it goes num multiplied by binomial num minus 1, which is 1. And it goes in here, passes in 1. Now, at this point, I is 1. So actually what happens there is that it puts in 1 there. Now 1 multiplied by 1 is, what's 1 multiplied by 1? 1. All right, so that effectively does nothing. So then you end up with 1 multiplied by 2 is 2. 2 multiplied by 3 is 6. 6 multiplied by 4 is 24. 5 multiplied by 24 is a lot less than I thought it was the first time round, is 100, whatever, what's 5? 120. 120. Okay, so now we're going to test it out. See, does it work?
We need to return num then.
Sorry?
With the first if we need to return num instead of 1. To get the answer.
No, well, you can return 1, or you could return num, because num is going to be 1.
No, but I mean to get the answer, print out the answer somewhere.
Oh, we're going to print out the answer up above. Okay. Right, so now, so I'm up here. Because Jason, you see, right, what you're doing is you start off with 5, and 5 multiplied by, it calls num minus 1, which is
Oh, we get all that.
4. Yeah. So it is going to print, it is going to do the calculation. Okay, and the last one it returns is 1. So it's,
I just thought that was a good spot to return the answer.
no, well, I'll show you now. It's even easier than that. That's actually what's produced. But 1 multiplied by 1 is 1, so you can ignore that one. All right. So I am going to go binomial 5. So the static void ex4, and that should be 120. Yeah. Okay. Now we're going to try a bigger number. So I am going to try binomial 20. That is 2.43 quintillion. I don't know how many quintillion, how many, so we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So it's 2 and 18 zeros, or it's 18 zeros. Okay. Now, if I do this one, binomial 65. Now, so here's the problem. It starts displaying in scientific notation. All right. Now you can convert that into a usable number. In actual fact, you can, yeah, it's complicated enough. I'm not going to do scientific notation. Fuck that. Life is too short for us to be using it. All right. So I'm not going to use scientific notation. Now, if you don't want it to display in scientific notation, what you need to use is the big integer class. Okay, so I'm going to put in a comment in here. So this uses recursion. Which is a method calling itself and keep calling itself until it gets to a base case and then exit the method. If a base case is never reached, then your program. Now, by the way, as I'm typing here, there's a way in this thing that you can copy and paste what's appeared on your screen. Do you know that? There is, yeah. I need to figure it out. I think it's fairly simple as well. I think I should share the application with you. So I'll have a look at that. It'll be very handy as I'm typing comments. You just can copy and paste it into your own. Okay. If a base case never reached, then your program can never finish. Okay. So this will result in a stack overflow error. Now, binomial numbers get very large very quickly, i.e. factor or binomial 20 is 2.43 quintillion, which is 2 and 4 18 zeros, not actually 18 zeros, but 18 places before the decimal point. Or this number to be precise. Is my imagination, or is there cold air coming out here somewhere? Anything cold there? No? I just got cold air coming out there. I know we get very large quickly, but I know which is 2 places for the, which is 18. 2 and 18 places before the decimal point, or this number to be precise. That guy. Okay. Now, this is a warning, as you can quite easily ask and attempt to do tasks in programming that would take more time than the entire lifetime of the universe to complete. Does any of you know of the, it's, I don't know, it's a Chinese or Japanese game called Go? Yes. What is there, 65 squares in or something like that?
There's more potential moves in a game of Go than there are the number of known atoms in the universe.
Yeah. Okay. So I think Go is made up of 64 squares on the screen. Okay. 64 squares. And it's just like, it's like a more complicated version of chess.
That was the first one.
Deep blue, yeah. So there's 64 squares on a board. And the amount of, and it's all these little beads. Okay. And they all occupy squares. Now, there is more moves in Go, and this is just 64 squares on a board than there is atoms in the universe. That's a lot. Atoms in the known universe, right? So that would take any machine more than the lifetime of the universe to calculate. All right. So, was it IBM?
Yeah.
IBM programmed a machine with artificial intelligence techniques. Now, it obviously couldn't calculate all the potential. It used other techniques. I don't know what techniques they used. I think that's probably how they learned shit. But it did, yeah. He was some Japanese dude and he was crying on television and everything. It's very funny, really. Those Japanese, those wacky Japanese. But what I'm saying is, it's very easy to do things that are going to be impossible. All right. So binomial 65 gets us a huge number. If you go to binomial 1000, it doesn't even try. It just gives us 0. Okay. Now, I'm just going to do one other binomial, except this binomial is going to use the big integer. Okay. Now, I'm going to call this guy factorial 2. Okay. So I go here, I go static. Now, this takes a big integer. I return the big integer. And this is going to be called factorial 2. Or sorry, binomial 2. Binomial 2. Binomial 2. And this time we're going to pass it in an int. All right? Now, I want to see how many times this big integer method is called. All right? Now, the basic premise here is if you have 1 and 1,000 places after it, okay, that means that this guy has been called right. I ignore that for a minute, okay? So I just need to figure something out here that I've done wrong. Right. Now, I'm going to be inside here. So we pass in int num. All right. Now here we go. String str num is equal to num, or even this one, it's going to be blank plus num. Okay. So when you put a string with the number, it all becomes a string. Yes, remember that? Simple way to convert from a string, from a primitive to a string. Now I'm going to go big integer. I'm going to call it big int is equal to new big integer, and we're going to say str num. Now, it's the exact same as this one up here, except we're using bigger numbers. All right, so if num is less than and equal to 1, okay, so this is what? This is the base case. What's it going to do? It's going to return new big integer 1. Now, else, I have 2 lines of code, so I need to put it in curly brackets. We go big integer big int 2 is equal to binomial 2 and we go num minus 1. So now you can't use ordinary symbols, ordinary mathematical symbols with big integers because they're just big numbers and it would take too long, right? It would take too long to do it. So we have, if you want to multiply, there is a multiply method, all right? So we go return big int 2 dot multiply big int. Now, I'll explain what's happening here. Now, so I'm going to pass in the number 65. Okay, so that's that. So then it converts it to a string. So big int is now 65. That's a big int is. All right, so it's going to keep working itself down to 1. It's not at 1. All right. Now, I create another big integer inside here, but it's going to be 65 minus 1. So that means that big int 2 is going to be 64. Okay, so what we get here is, so big integer is equal to binomial num multiplied by 2, and then it's going to return 64 multiplied by 65. And it keeps doing that. Then it goes multiplied by 63, blah, 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 blah. It goes all the way down to 1, and it prints off our number. All right, so we're going to have our number here. So we're going to try this one. All right, so we are going to go binomial. Now, as far as I know, this is the biggest one you can get, 984. It's binomial 2. Okay, now this produces this number. All right, now we want to see how long it is. Okay, so what we do is number is, and we go, call this binomial (984) dot, so it's binomial 2, 984 dot to string dot length digits long. Okay, so, oh fuck yeah. Wrong one, hold on a second. All right. So the number is 2,520 digits long. Okay, as far as I know, that's the biggest number in Java. I don't want to try any bigger number because I don't know what's going to happen. Okay, now if you want to see how many times it's called recursively, I create a variable here called static int, and I'm going to call it binomial count, or bino count is equal to 0. So each time this method is called, it's going to increment binom count by 1. So I want to see how many times it's called recursively. The binomial 2 method has been called over here by num count times. Now it's called 1,968 times. Okay. Now, so I'll just put in comments. So comment here. Show just how large we create a special binomial number method that uses the big integer data type, which can't use ordinary mathematical operators because they take too long. Simple as that, I presume. So plus multiply, etc. So you use their own methods, such as multiply. I think there's one called addition as well. Let me just quick check if it. Add. Multiply and add. Now, as far as I know, this is the largest number we can deal with. So it is 2,525 digits long. 2,520 digits long. Okay, and this method has been called 1,968 times. Okay, now when we come back from lunch, we're going to be using fork joins, and fork joins uses this recursion to work down to a base case. In our case, it's going to be worked down to 3 tasks. An individual worker, an individual thread, is only going to do a maximum of 3 tasks. If there's any more than 3 tasks, it's going to assign it to other threads, to other workers. Okay, we'll have 10 tasks. Now it does seem to, it'll find the most efficient way to divide up the tasks among 4 workers, 5 workers, 6 workers. And it does it all for you, not quite automatically, but it takes an awful lot of work out of it for you, all right? So now is as good a time as any to go across and get some salmonella, lunch. Okay, so I am going to pause that. I'm going to